Thank you all very much for coming to listen to me talk about voice lift system design. I'll introduce myself. My name is Andrew Francis. I look after applications engineering for SHURE in the UK region. And over the past 18 to 24 months, we've seen a significant interest in voice lift systems, which has been a really interesting little kind of project to be involved in, really. So I was asked to give you a short 20-minute presentation about what voice lift is, how you might think about designing a system, and the type of outcomes that you might expect to get from it. So let's have a very quick show of hands. And how many of you here are system designers? Integrators? Commissioning engineers? Mathematicians? Keep going, come on, let's keep it going. Cool, so at least one person here can probably take my place. That would be good. All right, let's carry on. Who's heard of voice lift then? Or is it just some ethereal thing that people are kind of hearing about on the grapevine? It's quite a difficult thing to explain because what we're trying to do is just compensate for the loss of audio over distance. So in our space here we have a PA system which is making my voice much louder than it would be naturally in this hall. And it's a one-way broadcast. I have a mic and none of you do, which is probably perfect because you have to listen and I have to talk, right? But for communication from you guys back to me, that's quite tricky. So we have to pass the catch box around if we wanted to do Q&A. Again, in a presentation point of view, that's probably the right way to do it. But in, let's say, a classroom or a boardroom situation, the need to pass around a microphone or a dedicated push-to-talk system per person can be a little bit of a barrier to fluent conversation. So the idea of a voice lift system is really to compensate for the loss of audio volume over distance. So in a larger room, there will be a point at which you can't hear somebody at the other end. So what we're going to do is use a microphone in the ceiling to pick them up and reinforce them to a small level to compensate. So it's not making anybody louder, it's just making everybody in the room, regardless of how far apart they are, about the same volume to every listener. Sounds pretty simple, but it's actually quite a complex and complicated thing to try and achieve. So a definition here of voice lift is an attempt to provide, as I've just explained, just enough sound reinforcement into a room so the furthest listener can hear just as well as the closest. So it's a very defined use of a system. And what it does, it only compensates for inverse square law, which on a very rudimentary level states that every time you double the distance between the sound source and the listener, you lose 6 dBs of power. And these are often deployed in AV conferencing rooms, or I've seen them used in all-hands flexible spaces or teaching environments where the teacher is in a large classroom. They might not want to wear a headset mic, but they want to travel around. And when they're assisting a student over this side, the students over this side don't benefit from the knowledge that they're passing on because they can't hear them. It does require DSP for signal routing and system adjustment. And the larger the system is, the more complicated that DSP design file is going to become. And it is much more complicated than traditional speech or reinforcement systems because we are dealing with multiple mics routed into multiple loudspeaker zones rather than just one mic into one zone. Voice lift really works well in some environments, and it really cannot work very well in others. The first rule is the room has to be big enough for the system to be able to cope with the gain before feedback barrier. So are you working in an existing facility with an installed system? Does this room even need reinforcement? You know, ask yourself the question, are we putting in way more time, money, and effort into this than we can really warrant? Because not all rooms need it. What microphones are used in the space? And what is acceptable? What is the end user expecting to get out of this system? If they are expecting a voice lift system to sound like I do with a lav capsule 3 centimeters from my face, they're definitely going to be disappointed with voice lift because it is not the same thing. And what environmental conditions within the space? What are the acoustics like? Is it very reverberant? Is it very noisy? Very reverberant and very noisy spaces are not good for voice lift. You want, in an ideal scenario, completely the opposite. Low background noise and very dead sounding. So the person who's talking, their sound isn't naturally going to travel to the far end because the energy is all being soaked up in the absorbent walls or the carpet. So you're absorbing all that natural energy quite close to them and then just trickling it in down the room as you go. So the introduction of voice lift into existing conferencing systems will affect the performance of the acoustic echo cancellation processes. So you might or probably will need to make some adjustments for that introduction of extra signal into the loudspeakers. Who likes maths? Nobody likes maths. Well, I'm afraid I'm going to have to teach you a small amount of maths to understand what we're trying to achieve here. So the inverse square law dictates that for every doubling of distance from the sound source, you get a 6 decibel drop in volume. Okay? So if your sound source is at S, point R is 6 dBs less, point 2R is 6 dBs less than point R, and point 3 is 6 dBs less than point 2. So by the time you get to point 3, you have significantly less volume than what you started with. Okay? And that's the same for PA as well. This is just the kind of framework that we're trying to put our system in. And now the same is true for microphones too. So for every halving of the distance between the sound source and the microphone capsule, you get 6 decibel increase of gain into the microphone. So you've got 6 dBs of gain advantage in bringing the mic closer, and you have 6 dBs advantage of every halving the distance. So once we start to put the mics further away and put the loudspeakers further away, you can start to see what kind of outcomes you might get from the voice lift. So if we calculate or measure a sound pressure level for a specific distance, we can use the inverse square law to determine the sound pressure level difference when the distance between the talker and the microphone changes. Okay? And as I've said, this works in both directions. If the talker gets closer to the mic, the volume goes up. If the listener gets closer to the speaker, the perceived volume goes up. So we have this idea of potential acoustic gain with needed acoustic gain. So any system will at some point run into acoustic feedback, whereby the volume coming out of the loudspeakers is bounced around the reverberant field and ends up back at the microphone. And that will cause a feedback loop. It's inevitable. All we're trying to do is pull advantages in how much we can take control of that feedback loop. So here's the equation. I'm not even going to read it out. It's very long. So the needed acoustic gain dictates how much additional volume you need in your space to compensate for the loss of audio over distance. And the potential acoustic gain dictates how much your microphone, amplifier, loudspeaker combination can provide in that space before it runs into feedback. So here we go, we need some distances. The distance to the loudspeaker, the distance to the first unaided listener, and the distance to the voice-lifted system listener, okay? So those, what's that, 4 or 5 variables gives us a number at the end of the calculation. And where the number of maximum number of microphones opens is equal to 1. So you can change that formula. If you have the maximum number of microphones open at 2, then you've got 2 sound sources into the system, which will inevitably reduce the amount of gain before feedback unless you deal with it with some kind of automatic mixer. Now, for people like me who kind of understand how a voice lift system works, but definitely can't do the maths, Shure have a calculator, which is very handy indeed. All you need to do is make some measurements in the room Fill in the various fields and a number will be spat out at you. And this number will tell you whether the system is capable of delivering a voice lift system. But let's look at loudspeakers first. In our space here, we have one loudspeaker zone. We have a pair of loudspeakers pushing audio out. You could maybe consider it two loudspeaker zones because you could have a left channel doing something different to the right channel. But that's it. That's all the flexibility we can provide in this system. Loudspeaker zones become increasingly important when you have a larger voice lift system and a larger number of microphones in it. Because what you want to do is say, right, audio picked up in this specific zone over here is routed only to those specific zones over there. And probably you want to give less loudspeaker reinforcement the closer you get to the actual talker. Okay, and we refer to this as a mix-minus system. So you're putting audio into the ceiling, but not where you're currently producing that audio from. And this requires DSP that provides a separate output for each zone. So you're going to need multi-channel amplifiers, or you probably now, the market is starting to move towards the idea of Dante routable loudspeakers. So here we go. Voice lift requires the output sound in any given zone and is devoid of any microphones that are active in that particular zone. All right. So the potential acoustic gain and the needed acoustic gain are equal to these two factors. So let's have a look at a very simple voice lift system. Zone 1 and Zone 2. So talkers in Zone 1 will be amplified only into Zone 2, and speakers in Zone 2 will only be amplified back into Zone 1. So this is the minimum requirement of a voice lift system. Okay? But it can be infinitely more complex. Here is an example of a 4-zone system, each zone consisting of 4 loudspeakers each. So talkers in Zone 4 will be amplified most of all into Zone 2, 2 back to 4, 3 to 1, and 1 to 3. So this is a room size of approximately 60 feet by 40 feet. So types and locations of loudspeakers are important. Now typically, in fact I can say in all bar one, I can think of voice lift systems that I've worked on and with. They've always been ceiling loudspeakers paired with ceiling microphones. And this is because we can get a nice distributed sound across the whole room rather than having a hot spot in the corner firing into the middle. As I say, Dante PO loudspeakers make a creation much easier because you're not having to run multiple lines of loudspeaker cable up into the ceiling and multiple channels of amplification as well. So if we think about microphone considerations which are suited for voice lift. If you benchmark any microphone against another one, the reference point is always an omnidirectional capsule. Now this will give you your very baseline, a critical distance between the sound source and the microphone, and also your potential acoustic gain. Then you can start to look at what advantages you can make in your potential acoustic gain by using a different capsule type, be it a unidirectional cardioid type capsule or more into a ceiling array directional lobe. So this PAGNAG calculator we've used a gooseneck or a boundary microphone very close to the talker. So here we can see the talker is only 2 feet from that capsule, but the nearest loudspeaker is 9 feet away. And the furthest listener is 18 feet away, and their listening distance is 5 feet from their closest loudspeaker. This kind of audio system design can provide 19.4 decibels of potential acoustic gain, which is 9 dBs more than the needed acoustic gain to compensate for the inverse square loss of volume over 18 feet. So this will work well. This will be a good voice lift system. But it relies on that microphone being fixed to the table, and it relies on it being in an absolutely solid position. If you start moving that boundary microphone around, then the whole system runs into different calculations, and that 19.4 could go down. So for example, if that microphone was actually 4 feet away, then you would lose 6 dBs of potential acoustic gain, which brings it closer to that feedback point. What about a ceiling flush mount microphone? So this again is a boundary. It's probably omnidirectional. And now we can see that if you put that type of microphone 6 feet away from the closest talker, all other parameters being the same, we can only provide 7.7 dBs of potential gain, which is less than the needed acoustic gain. So a system designed like this will run into feedback before any noticeable improvement will be made to the loss of inverse square law. So you can see here, you could put a lot of time, effort, and design work into designing something which fundamentally cannot work. What about if we look at something slightly different here? Let's go back one. Just for reference, what have we changed? That's 11 feet to the distance. So this is, yeah, this is running very close to feedback. Oh, did we skip a slide? Perhaps we did. Hold up a minute. What changed between when it was less than optimal? Here. So that's our boundary mic. 318.7566. Let's move along. 318.11. Okay. So we've moved. What we've moved here is the speaker at which the mix minus zone first goes into. So instead of reinforcing that speaker, that presenter into loudspeaker bang in the middle there in Z2, zone 2, we've only reinforced it into zone 3. And by doing that, we have bought ourselves some precious dBs of potential acoustic gain. So here we can potentially use 11.6 of gain, and the needed acoustic gain is 10.8. So this is now on the borderline of it being noticeable, but also being close to feedback. So what about a ceiling pendant type microphone? This is like a hanging gooseneck microphone, so this is the same except we've dropped the level of the microphone closer to the talker, which has bought us, again, some precious decibels. So in this scenario, zone 2 can be lifted to 11.2, which is only 0.4 of a dB above the feedback critical point. Again, if we move that to zone 3, okay, we don't have a zone 3. Let's change the microphone type then for a ceiling array. Ceiling arrays typically provide more gain before feedback than your pendant mics or your boundary mics in the ceiling because of the fact that they are so predictably directional and outside of where they're pointing to pick up the mic, you get a lot more rejection in their null point. So again, here is a calculator spreadsheet version of that very nice website one. But what this is showing here is that if your system, you were trying to use an Omni mic, you would run into your minus 2.48 dBs. However, all other conditions being the same, if you only swapped the microphone for a ceiling array with predictable pickup, you would then have 6 dBs, 6.5 dBs. So if the result of this calculator is less than 0, you will not get enough. So using a cardioid or an Omni, there's not enough, but using a seal array, you get 6 to 8 dBs more. Why is that? Well, if you look at these, in the best scenario, a supercardioid polar pattern from a hanging gooseneck mic is going to give you about 120 degrees of pickup. But with a ceiling array, we can narrow that down to almost to 35 in its narrowest or 55 at its widest. So that is why, okay, we're going to pick up audio from here or here or here. So we can become much more discrete about where we're picking up audio from, which is where we get our gains. So here we are, ceiling array microphones with a voice lift system, 2 active zones. And other considerations, EQ. Well, hopefully now that I've explained that gain structure is the most important thing to making the system work properly, EQ can help achieve better gain before feedback, but not significantly, okay? This is now where we're looking into, all right, it's working. We just want to get that extra bit, that extra bit, extra bit. Is anybody a cycling fan here? No? Yes? Dave Brailsford's Sky Team. You know about that? How they became like rulers of the Tour de France. They looked at this idea of everything we can make improvements on, even if it's using a bearing with 0.1 grams less weight in my bike. We can aggregate all these marginal gains to make some kind of massive improvement, or significant improvement at least. So this is, if you adopt the same approach with voice lift, this is how you're going to get to something working better than you did before. Just make a little bit of gain here, a little bit of advantage there. So EQ can help achieve better gain before feedback. And it can often improve intelligibility, which is why it improves the gain before feedback. So think about what frequencies are generated by the human voice, which are lost quickest over distance, and which are travel further. However, notch filtering, such as feedback controllers, can help to a point. But dynamic suppression is not recommended when using voice lift in a conferencing system with AEC, because the sudden drop in acoustic performance in the loudspeaker will cause a difficulty for that AEC algorithm. So a little bit of a system schematic here. If you're going to use 8 channels of microphones into a 2-channel or 2-zone system, you're going to have to split those mic channels, process it with one type of auto mixer to mix it for conferencing, and then send it through 2 additional gated auto mixers for mix minus into your loudspeaker. So scale this up, you can see how this gets quite complicated. Environmental considerations, I mentioned this at the beginning. Larger spaces have higher decay times, so therefore might not be suitable for voice lift, because all that extra energy that you're putting into the room from the loudspeakers is just bouncing around forever. If ambient noise is high, then you need more gain to overcome the noise in the room. So maybe just reducing the noise in the room is going to give you a better result. And poor acoustics, says here, equals poor results for voice lift. Let me correct that statement. Poor acoustics equals poor results for audio systems, full stop. Okay? So use absorptive materials such as carpet acoustic panels and ceiling tiles to improve the acoustics. Okay? And that's what I got for you. Do I have any questions? You're all going to go out there and deploy amazingly successful voice lift systems now. But really the point of it is that if you're building a classroom type environment where you've got people coming in and coming out and you don't have time, or you don't want to give each person or even the presenter themselves a headset or a gooseneck mic, the other traditional problem you get is if you have a podium at the lectern with a microphone, the tutor's standing there giving their lecture and they go, oh, right, I'll go and talk to you over here, and all of a sudden they can't be heard by anybody anymore. But with a ceiling array voice lift system, you can create pickup across the stage so that when they move away from the lectern, they can still be picked up and they don't have to wear a headset mic. So in certain situations, it's really, really useful. But it's not suitable for everything all the time. If there's no questions, I'll say thank you very much. Obviously, SHURE are here. We have a booth over in Hall B. I think Hall 3, B100, the very big black and green booth. Come by and say hello. Talk more about voice lift or anything else that we've got going on the stand. Otherwise, I'll bid you a good ISE. Enjoy the last one in Amsterdam, and I'll see you in Barcelona next year, hopefully. Thank you very much.